it comes to parallel circuits, we once again want to be able to figure out the equivalent resistance or the total resistance for the entire circuit. So to get a better understanding of that, we need to first realize that as I add more and more resistors in parallel, I'm not changing the number of resistors any one electron has to go through. That's still only one resistor. I'm providing more pathways. And when you provide more pathways or more options, much like in the supermarket checkout lane or the toll booths on the highway, you actually decrease the resistance. So by adding resistors in parallel, we decrease the resistance. And therefore, if you'd like to calculate the total resistance of a parallel circuit, you will commonly see it written this way, but hold off 1 second before you copy this down. I'm going to show you a simplified way to write this. So this is what you'll commonly see in a textbook or online. It's the inverse of the total resistance in a parallel circuit is the equivalent of the summation of all of the inverses of the resistors in that circuit. It's okay, but you have to realize when you add all those up, you then need to reduce the numerator to 1, and then what's in the denominator is equal to the total resistance in parallel. I find it all a bit confusing, so I typically write it this way, and this is how I will list it on your equation sheets for you. If you would like to know the total resistance of a circuit that's wired in parallel, add up the inverses. Raise R1 to the negative 1, add that to R2 to the negative 1, plus R3 to the negative 1, and so on and so forth for however many resistors in parallel you have. When you get that result, raise that result to the negative 1. So you're doing a bunch of raising things to the negative 1, but first you add up all the inverses, then you take the inverse of that answer. It's essentially the same thing as what's written up top, but I think it's quite a bit easier to try and figure this out. If you want to apply this to then solve a problem, the 4 steps you're going to want to follow are fairly similar to the series circuit examples. We're going to start off with the same first 2 steps. Calculate the total resistance using that equation we just saw. Determine the total current coming out of the battery. The difference here is with a series circuit, the current is the same everywhere, so we fill out that current column. The difference with a parallel circuit is the voltage is what is the same everywhere, because no matter where you go through one and only one resistor. It's the current that splits into parallel, so we can no longer just apply the current throughout the entire current column in our VIRP table. But we can do so with the voltage, as the voltage in a parallel circuit will always be the same as the voltage of the battery. And last but not least, we then need to calculate the current and the power for each of the resistors. Those will be the 2 spaces that are left. Following videos, we'll go over a few examples so you can really see how to use that equivalent resistance calculation and how we can fill out a VIRP table for a parallel circuit and therefore know all of the currents, voltages, resistances, and powers associated with the entire circuit, as well as any individual resistor we may desire to have some information about.